So before we begin, let me revisit something that I'd like to talk about. Now that we have quantized our theory, we should really go and check that our operators actually satisfy what we conjectured them to do all along. And we'll find a surprise there. So under some Lorentz transformation, suppose we have some operator on our Hilbert space. That operator should change by some unitary transformation. So U of lambda are the unitary infinite dimensional representation of the orthochronous Lorentz group, proper orthochronal Lorentz group. Now, so by definition, this is the transformation that's going to happen. Now, if you look at psi, the operator, it's got this integral, but that's not an operator, that's just a number. And there's a sum over spinors. They're also just, they're not operators. So, sorry. The operator bit is the creation of the annihilation here. And the U operator will act on this annihilation operator. And then we have the plane wave part. And similarly, for the V spinors, we have the operator acting on the creation operator for the antiparticles. Right? So we expect, and you can check, that U of lambda acting on Bs of P should transform this full momentum by Lorentz transformation. So this should become Bs, of lambda P. And similarly, U of lambda acting on, say, C dagger S of P, U inverse of lambda, should give us C dagger S of lambda of P in P prime. P. Sorry, not P prime. Where do you call it P prime? But right? So we expect that. So nothing here should be controversial after yesterday's tutorial. That these guys, the unitary operators, act on the creation and annihilation operator. So let's call lambda of P, P prime, just for convenience. Then in the right. So we can now replace this guy's here by Bs P prime, and this guy here by C dagger S P prime. Now the measure for this Dirac field is Lorentz invariant. So if we put primes on all the p's in the measure doesn't change, right? because this is a Lorentz invariant measure. And then we can say, well, we can invert this. Then lambda inverse of P prime is P. And using that, we can convert this into lambda inverse P prime dot x and convert this as well as I lambda inverse P prime x. And then also replace the p's here by lambda inverse P prime. P's here by lambda inverse P prime. So I have converted everything to P prime and used the fact that the measure is Lorentz invariant to write it in terms of P prime. Okay? Now remember that the way we derive the spinors is by Lorentz boosting them. So we should have U of S lambda inverse P prime as S of this acting on US of P prime, which is S inverse of lambda. And similarly for V. Okay? So for V, we should have S inverse lambda of US of P prime. Now, if you use these expressions and here, then the result that we get is this. We get that U, well, let's write this again. Psi of x, when it's transformed by a unitary transformation corresponding to the infinite dimensional representation of the Lorentz group, we get S inverse of lambda psi of lambda x. Okay? Because we can factor this out. Remember the classical field, so this is an operator, let's stress that. In the classical case, under Lorentz transformation, this guy transformed like right? Remember that? And in Dan's part of the course, for the classical scalar field, the corresponding transformation was just, there was no spinor index, right? So here we see that the operators actually, when you quantize them, they actually do not transform the way that the classical fields transform. In some sense, they transforms in the opposite way. And that's something that's a little kind of noticed fact that you should be aware of. So, these are really different objects. This is just some classical field configuration. And, its transformation is like this, just from looking at it as a function. But these guys are operators which will act on Hilbert space to create particles. So they're actually very different things, okay? But I just wanted to make sure that not many textbooks talk about it. Only Peskin mentions it in chapter 3. Okay. Do you have any questions? All right. So today, we are going to start with time ordering, causality and time ordering of Dirac operators, of fermionic operators. So So QFT is a local theory. This is reflected by the fact that our fields are space-time points of space-time, are functions of space-time points. And if you have an observable in QFT, so this is an observable, then you cannot simultaneously observe two observables. They cannot influence each other if they are space-like separated. So this is translated to the fact that the commutator of two observables is 0 if the separation is space-like, right? Remember, our metric convention is plus, minus, minus, minus. So like an interval squared minus less than 0 is it's a space-like separation. So this is the statement of locality in QFT. Pictorially, this means that if this point is x and this is the point light cone, then y is somewhere outside the past or the future light cone. So in a bosonic QFT, this condition is easy to implement because all we need to check is that our scalar field, suppose we have a real scalar field theory, that this is 0 for space-like separations. However, for fermions, this is not true. So commutators of fermions not 0 at space-like separations. I think Matthew Schwartz does an explicit calculation of this, but I can't remember. I think, yeah, Matthew Schwartz actually shows this somewhere. So fermions don't seem to automatically satisfy this condition. But we know that the observables of fermions are bilinear in the Fermi field. So an observable created out of fermion has this form. So you get some Dirac field and something like this, where gamma is some combination of gamma matrices. Okay. I'm going to raise this board up there. I know it's hard to see up there, but hopefully you're done by this time. But hope is there because it's a bilinear in fermion and its conjugate field. The commutator of two observable can be decomposed in terms of anti-commutator of the fermion fields, right? So you know that if you have commutators of say something like this, you can actually write it in terms of anti-commutator of the individual operators. So all we need to do then is to actually verify that the anti-commutator of our fields are 0 at space-like separations. Okay. So let's verify this for the Dirac fields. So you can show that the anti-commutator of psi n psi bar is given by I slash delta x plus m. Take the AB element of this matrix, acting on this combination of two two-point functions. Where I think this two-point function you saw in Dan's part of the course, this is not very hard to work out. You use the commutation relationship, but keep in mind that these are like function of not just space variable but also time variables. Where this dx minus y is this function. Now, I want you to take a few minutes, say maybe 5 minutes, and show that this implies that the anti-commutators psi A and psi bar B of y is 0 when this is space-like separated. The hint is that for space-like separations, you can choose a reference frame in which the two events are simultaneous. Okay, so let's go and let's look at this. So show that this thing is 0 when x minus y is squared is less than 0. And the hint is use this, okay? I'll drop another hint. You basically have to show that this is 0. You guys should talk to each other if you need to, okay? Don't be an island. Sorry?
The reasoning for that first and second line?
This?
Yeah, and above, the line above, what is that? Yeah.
Oh, so what I'm saying is that if you have an operator which is composed of more than one operator, say this could be psi bar, this could be psi, and this could be something else, then commutators of composite operators can always be expressed as, anti-commutators of the individual operators.
This is always true?
Yeah. This is just you basically do this, right? AB of C is ABC minus CAB. And then I always get this wrong, but I think you try ABC plus ACB. So you just add this and you subtract the same thing. Then you get right. So basically that's the.
You have this there too. And then for one of them, you take that P goes to minus P. Then the only question I have is that, like, you're assuming that it's like the same both these.
It's a dummy variable, so you can put them both in the same.
All right. We need somebody to volunteer the answer. 0, yes. How do you get there? We were looking for a volunteer, so you came right in on time. Can somebody explain why it should be 0? Yeah?
So because we can choose this frame where x naught equals y naught,
Yeah?
we can get rid of the time part in our exponent and only have 3 vectors multiplying things. And because of this, we can just swap p goes to minus p for the second part and see if they're actually equal. So
Right. Good. All right. Very nice. So one thing we notice is that our function is actually Lorentz invariant. So if we can show it to be 0 in one reference frame, it has to be 0 in every reference frame, right? That's something that Neil taught you. So what we do is that in the second one, we basically set x equals, if you look at the second one and we set x equals to, x naught equals to y naught. And then as Katerina was saying, we have our exponent is now only involves, say, 3 vectors. So now if we do this switch in the, do this change of variable, our integration measure is invariant. So we have the same thing, but here we have minus I, or say, so plus I, p dot, now x minus y, which is d of x minus y. So for space-like separations, these two things are equal, and therefore they cancel out. Okay. All right, very good. So for the rest of this lecture, we will try to obtain these two, these would be our lesson objectives. First, we want to define what the Feynman propagator is. For the Dirac field. Second, we want to derive Wick's theorem, at least the two field case for fermions. And we won't have time to get into this today, but we will get into this next time, is we want to derive the Feynman rules for fermions. But we want to use a particular theory, which is the Yukawa theory. Now for this, I'm going to use slides. I put the slides within quotation, but what I'm going to do is that I'm going to use the lecture notes. But I'm not going to write everything out on the board because it is excruciatingly boring and long to deriving the Feynman rules. So if we don't get into this today, I would suggest that you read that part of the lecture note before tomorrow so that we can follow along, okay, sing along. And okay, so Feynman propagator for the Dirac field. So before we can talk about the Feynman propagator, we need to talk about time ordering for fermions. So recall for bosons, if you have two Bose fields, time ordering meant you push the one in the past to the right, so given the anti-commuting nature of fermions, this definition of time ordering turns out to be wrong. And you've guessed it, you need a minus sign. So let's see that. If you don't, then you arrive at a contradiction. So let's see that contradiction. So suppose we have two Fermi fields, psi and chi, and they just happen to anti-commute. So there is no delta function or anything here. They just happen to anti-commute. And we can find such fields. They can be just two non-interacting fermions. Now suppose let's suppose that x naught is greater than y naught. So we know that psi a of x and chi b of y anticommute. So if you now apply time ordering to this, our old notion of time ordering. By the way, this minus sign, I think there's a typo in the notes. I didn't put this minus sign, so it should be there. So according to our old definition of time ordering, this should just remain what it is. But on the right-hand side, we should switch, these guys should switch places. So we have a quantity which is equal to minus itself, which means it's 0. There's no reason to assume, we have not assumed that psi a of x, this is 0. So this is in general non-zero. Therefore, our definition of time ordering must be wrong. So the correct definition of time ordering for fermion is then fermions should be this. Note that this means that inside the time ordering, when you switch to fields, you pick up a minus sign, right? All right? So once we have defined time ordering, we can now define the Feynman propagator. So I think it was Dyson who told Feynman that, or maybe somebody else, that what he was working with are Green's functions, and he should look up the literature on Green's functions, and Feynman refused. So the Feynman propagator for fermions, it's a 4x4 matrix. It has spinor indices. So sometimes you will see they won't write the spinor index, but it's implied. This is the Feynman propagator. So according to our definition, if x naught is greater than y naught, or minus psi bar b of y, psi of a of x, if y naught is greater than x naught. So what's the interpretation of the Feynman propagator? So it's the same as in complex scalar field theory. So suppose that x0 is greater than y0. So we are in this case. Recall that psi bar has the creation operator of particles. And psi has the annihilation operator of particles. So what it means is that a particle is being created at some space-time point y, and it propagates into the future at the space-time point x and is annihilated there. However, we can say that psi, you can observe that psi a has the creation operator of antiparticles. And psi bar has the annihilation operator for antiparticles. So we can very well say that the Feynman propagator represents an antiparticle being created at space-time point x, and it propagates backward in time and is annihilated at space-time point y. Both are equally valid interpretation. Okay. Outside the light cone, because what is past and the future is not something that's a frame-dependent statement, so that interpretation becomes ambiguous. Well, it's already a bit ambiguous. So I think, Feynman had all kinds of picturesque way of thinking about things. An electron comes and it gives off a photon, and then it scatters back into the past, or something, and then the photon decays into, and you can have similar interpretation here and stuff like that. Anyway. Okay, so let's look at some expression for the Feynman propagator. It'll be slightly different from the expression that you saw for the complex scalar field. So it's worth looking at. So if you use the field expression for the fields, then it's very straightforward to show that this is now, using the completeness relationship, we can write this in terms of moment, this particular operator in momentum space. Well, we can basically write this as so we are pulling this operator outside. When it goes inside and acts on this, it'll drag down a factor of IP minus IP, and and you'll get the usual completeness relationship. And similarly, if you compute psi bar B of y, psi of A of x, you find minus I So for the two different cases, we have two slightly different expressions for the Feynman propagator. However, there's a very neat covariant expression for the Feynman propagator. By covariant, I mean it's something that it applies to both the cases where x naught is greater than y naught and x naught is less than y naught. And it's analogous to an expression you saw, hopefully, in the complex scalar field. Do you see that? Without. Okay, let me write down and then write down the expression and then ask you if you have seen this. So the Feynman propagator can also be written as d4p integral. So it's manifestly covariant and symmetric between x naught greater than y naught and x naught less than y naught. Okay. However, as this expression is actually not well defined because there is a pole at p squared equals to m squared. So until I tell you how the p0 integral is done, this expression is not well defined. And we are now going to do the give you prescriptions about how that p0 integral is done. So I'm going to do case 1 explicitly. The case is x0 greater than y0. So we rewrite the Feynman propagator. So I'm going to show that the covariant expression leads to the more explicit expression, the previous expressions that I gave. So this, the numerator, I'm going to separate the time part and the space part. And then the denominator, I'm going to lump the space part momentum and the mass into EP squared. Then I'm going to separate the time part of the exponential from the space part. Now, Feynman's prescription for this is that when you're doing the integral on the p0 plane, you've got two poles. There's a pole at minus EP, and there's a pole at plus EP. And his prescription is you go along the real axis, the real line, and you go below the negative. And then you go above the positive pole. And then you want to close this contour. This factor determines whether you have to close the contour below or above, because you want to use the Cauchy residue theorem, and you want the contribution from the way you close the contour on the complex plane to vanish. And if you look at this, you see that if P had a big negative infinite part, then this would actually go to 0. And therefore, you have to close the contour in this way. Where, of course, I mean, this is a contour which goes to infinity. So the radius is infinite. So, so if you use Cauchy's residue theorem, I assume everyone kind of is familiar with that. Okay. We didn't do complex analysis this year because for the last few years, we found that the students actually knew a lot of complex analysis, so we didn't do it in the front end. But if you have any questions about the residue theorem or stuff like that, come and talk to me. So the 3 momentum integral is going to stick around. And because this contour is going at a clockwise sense, we pick up a minus sign, and there's a 2 pi I from the residue theorem. And you have to multiply with the factor that blows up. And we have our numerator and the denominator now has P0 minus EP, P0 plus of EP, and e to the power minus I P0, X0 minus 0, and e to the power plus I P, 3 vector P. Okay. So these guys cancel. And then when you actually put the value of P naught equals to EP, you get B cubed of P, 2 pi cubed. One of the 2 pi's is canceled by the 2 pi coming from the residue theorem. And the minus I and the plus I gives you plus 1. Your P0 becomes EP and plus PI and this you can then rewrite as P slash plus M by 2 EP. Usually we write it with this guy, P dot X minus Y. Here P slash plus M, it can be written like this by factoring out this operator. And so similarly, for so for the case of y naught greater than x naught, you can verify that the contour is like similar to the case before. You go below this minus EP, and you go above this. But now you have to close the contour upstairs. And so previously, when you did that integral, you picked up the residue from this pole. But when the other case, you pick up the residue from this pole. It is somehow symmetric between these two residues. Often you'll come across another version of the Feynman propagator. So the version that we have written here is with those prescriptions. Okay, before I give you that, the alternative form, there's a clever way of encoding the fact that this part of the contour, the one that goes along the real line, always bobs around underneath this pole and bobs above this pole. The clever way of encoding that in the expression is to put a plus I epsilon here, where epsilon is a small positive quantity. Why is that? So if you now look at the denominator, it changes the position of these poles. It pushes the pole at negative EP slightly off the real axis in the imaginary direction over here. So this is now your, so EP, say, this is, say, epsilon, so plus I epsilon. And this thing is pushed down to this point, so EP minus I epsilon. And then when you've done this, all you have to do is to just, do the integral along the real axis. And depending on whether you close it down in the lower half plane or the upper half plane, the correct pole is included in the contour integral. So this is Feynman's plus I epsilon prescription. Okay. So there's another way of writing the Feynman propagator, and you'll find it quite often used in textbooks and calculations. So this is basically the other thing is that this plus I epsilon is always there, but we will not explicitly refer to it, but it's always there. Okay. So using the fact that the denominator can be written like this. It's often, the Feynman propagator is often written in this way. So the Feynman propagator, I should let me put back the space-time dependence. So in momentum space, it's then given by so compare it with the propagator for the scalar field theory, the complex scalar field, for example. You had something like, right? That's what you got. The scalar field theory. So let's start with Yukawa theory. Some preliminary comments about Yukawa theory. And Yeah, let's come here. Okay, before we move on to Yukawa theory, any questions from that part? All right. If not, so Yukawa theory is one of the first successful quantum field theories. It was before quantum field theory became fashionable. Yukawa was a Japanese physicist. Quantum field theory was virtually unknown in North America until after the Second World War. It was Freeman Dyson who brought quantum field theory to North America. He had learned quantum field theory at Cambridge from one of the refugees who ran away from Hitler. And when Freeman Dyson came to North America with a scholarship, he taught Feynman quantum field theory, and he taught, I think it was Hans Bethe quantum field theory, and a bunch of other people. He told me this earlier this year. I went to interview him for a personal film project. All right. So Yukawa was in the 1930s. He was trying to explain or describe the short-range, extremely short-range interaction in nuclear physics. So in 1934, Yukawa proposed that nuclear interactions, or I guess interactions between nucleons, is mediated by a heavy, well, he used a pseudoscalar particle that he called a meson. So this successfully described the extremely short-range interaction of nuclear physics, of strong interaction at the level of nucleons. It's a very interesting theory because it has been generalized. It turns out that the Yukawa theory is an example of a renormalizable theory. And therefore, there's a generalization of Yukawa theory. Or there's a generalization of the Yukawa interaction that's relevant or important for the standard model. So the interaction and as well as the mass terms of the standard model is given by kind of a Yukawa type of term. And you'll see that in the standard model course. So what is the Yukawa theory? So the Yukawa theory is the theory of nucleons. So it has our nuclear physics. It has a part which describes the fermions. So let's just take one type of nucleon and its antiparticle, and it has a part which is the scalar, the meson, and then there's an interaction term which I'm calling L-yuck. So in our case, we are not going to deal with a pseudoscalar particle because we are just doing the Yukawa theory to develop the Feynman rules, and we don't want to make complications, unnecessary complications. So our L fermion is going to be just the Dirac Lagrangian. So the small m is the mass of the nucleon. L of phi is a real scalar field. And then the Yukawa interaction. Okay, pop quiz. What's the dimension of a scalar field? What is the mass dimension of a scalar field? 1. What is the mass dimension of a Fermi field, of a Dirac field? 3.5. So what is the mass dimension of lambda? 0. Because the mass dimension of the Lagrangian has to be 4, so that the action is 0. So this means that, so for perturbation theory, we assume that lambda is positive and small, and then lambda has mass dimension 0. Note that the Yukawa, this Lagrangian has a global phase symmetry. If I take the fermions and rotate them by a global phase rotation, then that's a symmetry. So that means that there is a conserved charge, and that conserved charge is nothing but the nucleon minus antinucleon number. That's our conserved charge. So in the standard model, there are 2 global symmetries, and these global symmetries will correspond to the conservation of baryons and the conservation of leptons. But in the standard model, those global symmetries are accidental. Global symmetries are very rare in nature. So people didn't really sit down and, and create a model which would actually have those symmetries in. Once they've observed, they've put in the other symmetries, the gauge symmetries, and and looked at all the terms that are possible. It turned out the standard model has a B and L symmetry. So we want to derive the Feynman rules from Yukawa theory. So there's an analog of the LSZ theorem or LSZ formula for the fermions. Okay. I'm not going to go into that, but I'm just quoting that to say that in scattering processes, we assume that in the asymptotic past and the future, our in-states and out-states are consisting of particles which are widely separated from each other. Therefore, they are non-interacting. And that the in-state and the out-state are created by acting with the creation operator and the annihilation operator on the free vacuum. So we are interested in 2-to-2 scattering. That will give us the Feynman rules that we need. So we want some our outgoing particle will have, say, in case of nucleon scattering, it'll have some momentum P1 and spin S2, and momentum P2 and spin S2. And this is our out state, and it's in the far future. And the in state is, say, K1 R1, the 2 K2 R2. So sometimes I will use 3 momentum notation to distinguish this from the spin part. But I won't be very consistent. So this is a Schrodinger picture expression. So in the Heisenberg picture, states do not depend on time. So we have our out state is some state like this, and it's related to the in state through a unitary operator, which we call the S matrix or S operator or scattering operator. I was an undergraduate once when I came across the S matrix in quantum mechanics, and then I was reading a book by Heisenberg, and he was talking about, in the introduction, the S matrix of the universe, and I got really scared, I remember. So we are interested in scattering process. So we're interested in processes where something actually happens, where 2 particles go, they do something, interact, and then 2 particles come out. It can happen that 2 particles go and they completely miss each other. And that's not what we're interested in. So the scattering matrix can be decomposed into an identity part, which says nothing has happened. And one part, the other part is the T part. It's called the transfer matrix. So I'm going to try to use T both for transfer matrix and for the time ordering operator. The transfer matrix will not stay around for long, so you don't have to invest in it too much emotionally. We are going to use the symbol M for it. So if you look at so we are interested in the transfer matrix part, and we are going to write this transfer matrix in terms of a 4 momentum conservation, and this is going to come out of the theory, as we shall see next time. So the overall 4 momentum is going to be conserved. And there will be a complex quantity, which we call the amplitude. And it's really this thing, the amplitude, or this is sometimes called the amplitude, or so we shall compute that using the Feynman rules. Well, we're computing the whole thing. So using the LZ reduction, and also the fact that we can express we can use the Dyson formula to express the interacting vacuum as a in terms of the free vacuum using all the machinery that Dan kind of developed, which I'm not going to go through. The thing that we want to do is following. Remember that when you use all that machinery, the vacuum bubbles, the disconnected diagrams, those are all taken care of. So what we want is our transfer matrix is going to be given by, you take the limit of t going to this, and so we have this state. I don't know why I wrote 0 there. And there's going to be the time ordering operator here. So this t and this t are not the same. And inside, we are going to have the Dyson series. This t and this t is time. This t is the transfer matrix. Let me put something else here. And this t is the time ordering operator. There are 3 t's in this formula. And okay, this small t is time. This is the interacting Hamiltonian in the interaction picture, and that's why it depends on the t. And this is the asymptotically state in the asymptotic past. And what all the machinery that Dan developed tells us is that to calculate this thing from here, we have to only consider the parts where they're the connected and amputated. So for the external lines, we actually don't want, at least at tree level, we are, we don't want to consider self-interaction of those particles. So to actually calculate something, this looks a little bit daunting. To actually calculate something, we have to know how to apply how to decompose the time ordering operator of our Fermi fields, Fermi and Bose fields, in terms of normal ordered operators and contractions. In other words, we need Wick's theorem for this. You have seen Wick's theorem in the bosonic context. We now come to Wick's theorem in the fermionic context. So Wick's theorem turns out to be the time ordering is the normal ordering of this, guys. We have already defined normal ordering with a minus sign last time, where I made a minus sign error. And then a contraction, which I will define shortly. So the contraction is defined in this way. It's the anticommutator of the part of psi which contains a positive frequency. The plus is for positive frequency. Remember, for the positive frequency, with the positive frequency came the annihilation operator. Okay. So this is not dagger. And psi bar of minus B of y. This is the negative frequency of psi bar. Remember that had the creation operator for the particles. So this is when x naught is greater than y naught. And there's a minus sign here. There's a psi bar plus. If y naught is greater than x naught. So you can show that this actually means that the contraction is actually the Feynman propagator. Probably can't see it, so let me erase this. Also, to be consistent, we need to define contraction between two psis, and that's defined like this, and then you can calculate that to be 0. And the contraction between So let's end with an exercise. Suppose that x naught is greater than y naught. Then just for convenience, write psi in terms, so this is part has the annihilation operators, and this part have the creation operators. Similarly, psi bar can be written like this. So now the question is, can you show for the x naught greater than y naught, Wick's theorem holds, okay? Using that definition of a contraction, okay? So we have about 8 minutes, so let's take 5 of those minutes to try to work this out. Okay? So take the case where x naught, can everyone see this? Or is there too much glare? Okay, good. This is an good exercise to do because it's one of the very often asked questions in the interview. So you're actually preparing for the interview right now. Okay. Did anyone? Was anybody able to show it? Maybe give 1 more minute. All right, somebody wants to come and show it on the board? We need a volunteer. Or do you want me to draw some straws? All right. Let's look at the explanation because we have 1 minute left, so I'm going to resort to technology. Marg, can we have the board down? Thank you. I am connected. I'm going to try again. Oh. Disaster. Okay, so I guess. Oh, don't worry. Then I'll just use the Blackboard. Okay. Oh, sorry. Technology failure. So. Okay, you can raise the Blackboard. Yeah, thank you. So what we want to do is we want to hang on. Right. So the time ordering of psi and psi bar is just this. We can write this as psi plus psi minus and psi bar plus psi bar minus. And if you just expand this out, psi plus psi bar plus psi plus psi bar minus plus psi minus psi bar plus psi minus psi bar minus, then you see that all the terms are actually already normal ordered except this guy, right? So what we want to do is then we want to add a normal ordering version of this term. So, and because we have added this term, we have to subtract the same thing. The stuff over here. Now you see that this guy and this guy can be combined into a commutator. And the rest of it is actually a normal ordering of my original expression over here. So this should be an anti-commutator. And this proves Wick's theorem for the case x0 greater than y0. So it's elementary. And then similarly, you can, if y0 was greater than x0, then you would have this guy on the left side and this guy right side, and doing this expansion, you get a different anti-commutator, and you get the second line, okay? All right, let's stop here. And next time, I will give you, if technology permits, I will give you a presentation on how to derive the Feynman rules using Yukawa theory.